PhD defense. Title of this is Sensory Relevance Models. I'll get into what exactly that particular jargon means in a little bit. Yeah, this is the highlight of the last 5 years of my life, so let's see how that goes. And yeah, you know, it's not a solo journey, so small list of people there who helped out along the way. So, machine learning. The topic of this in general is explaining machine learning. So what machine learning is a way to teach computers to perform algorithms that are difficult to program imperatively. So traditional computer programs, you set up a serial set of instructions, it executes that, somebody has to very carefully craft that pipeline of instructions, and you turn some set of program inputs like an image into an output. Now for some transformations, like turning an image taken during daytime into an image at nighttime, it's very difficult to write a program that way that works effectively. So what machine learning is looking more at examples of the transformation you want and trying to imitate that operation, right? Trying to reproduce that and generate a program based off of example more than an explicit algorithm programming. Classification is also a large use of machine learning, and that is in fact the focus of this dissertation. The way a lot of these machine learning algorithms are implemented are neural networks, which is basically a linear algebra machine with various nonlinear activation functions. There's a theorem that if you make one of infinite size, it can express basically any mathematical function with arbitrary precision. There are some practical issues there. And deep learning just refers to stacks of these neurons that are sufficiently deep to merit the title. And that to use this neural network to go from some input to some output and realize the transformation. And then the other vocabulary I want to mention real quick is human in the loop. So traditional machine learning, like image classification, you start with, this is a picture of an apple, this is a picture of an airplane. You have 10,000 of those examples or whatever, and then you put it through your machine learning algorithm to learn the transform. Human in the loop refers to kind of a next step where you then look at the output of that classifier and a human annotator judges the results of that algorithm and says, yes, that's good, or no, it could be improved like this. And it's kind of a feedback loop for improving the way that the machine learning algorithm works. So we will be getting into that more. Classification is the focus here. If you show a computer program designed to take an image, and you write that program so that it gives you here a confidence distribution, basically, of different types of objects. These are examples on ImageNet, which has 1,000 different types of object that the picture could be of. Then it gives you some confidence distribution saying, that's a picture of a mite, or that's a picture of a container ship. And all you get out of these machine learning algorithms is that final confidence information. The top 4 here were correct guesses. The bottom 4 were incorrect guesses. And it's not clear from this why, I think that one may be that example, but this one, we all know convertible would have a hood. But maybe we're less familiar with mushroom identification. And it's not clear why the agaric categorization was put above the generic mushroom category, which was correct in this. And so if you have an app on your cell phone, things you can eat to survive in the wilderness, if you're hiking around in Alaska, you're hungry and you want to eat something, take a picture with your phone and it says edible, and that's all the information you get. Should you trust that, right? Do you want to eat that thing when you know that an incorrect answer from the computer algorithm looks, if you don't know the problem, an incorrect answer looks the exact same as a correct answer. Without domain knowledge, you can't really differentiate between those two. And so explaining why the decision that the computer generates was made, people like to not just accept advice. We want to know the reasoning behind the advice. So that's the focus here. So explainable machine learning is basically the name for this study for explaining machine learning. It's the title. And I'm going to talk about 3 state-of-the-art methods. 2 of them are shown here. At top is LIME, locally interpretable model explanations, I think. And Ribeiro et al. Proposed this in 2016, and what it is they take an image. So here we have a chest X-ray of a lung nodule, a tumor, and it's this shadowy area in the middle. And what Lyme does is it breaks the image up into a grid, and it basically plays, if I take out this spot in the grid, does the classification get better or worse? And it does that with all these different superpixels, they're called. And at the end, what you get is a mask of these are the regions that were deemed most salient, were deemed most important, right? So if the computer labeled this a lung nodule, the reason it labeled it a lung nodule was most affected by the unmasked regions of that far right image. GradCam is a similar thing, in a manner of speaking. So a lot of neural networks are broken up into what's called a convolutional neural network. And what that means is that you're taking a mathematical neighborhood and you are convolving that, you're sliding that operation across the whole image, and you end up with this grid of computation, basically. And what GradCam does is look at a very specific layer of that convolution and evaluates how that convolution affected the final output. It generates a little heat map showing you if you change pixels in this region is going to have the greatest impact when it comes to changing that lung nodule classification to a non-lung nodule. So both of these, the point here is to highlight what's important, right? Now this one arguably misses the mark entirely. This one, you know, it's kind of focusing on the lower right of the nodule, but it's difficult to say why that's important. Like it's pointing at it, but it's not really giving you more information than that. And these are both post-hoc methods. You look at a neural network that already exists with those. People have also done architectural methods to improve the explainability of these. So this is a picture of the activity at different layers in what's called an attention network. What an attention network is you generate a mask that you multiply the input image by. So the goal here is you want to weight parts of the input that are more significant, right? You want to say, this is the salient object, right? This frog here. So those are the pixels that should have the most effect on the output of the network. You actually get an accuracy boost through attention models, so that's cool. And you also get this mask. But it's kind of the same thing as the last slide, where even if this lines up, right, like clearly the red regions, which are the parts that the network's paying attention to, they highlight the deer here, right? They're hitting the right objects, but the output could just as well be frog, and you'd get the same mask. Now that would be a wrong answer, but this doesn't tell you if the answer is right. It's only pointing you at the important data. So this is one of two flaws that basically all state-of-the-art explanation methods have when it comes to explaining these machine learning algorithms, is that they just give you a heat map. They will point you at the part of the image that is maybe important, but they don't actually highlight the features in that segment that are important. It's like if you had word editing software and you get one of those squiggly red lines, and there was no mouse over it. Didn't tell you anything. It just put the squiggly red line. That's going to be a really hard problem to fix without additional information. Again, could have just been a frog as easily. So that's flaw number one of existing explanations. They all boil down to this heat map, which can point you at a problem but not necessarily tell you anything about how to fix it. So switching gears for a minute, adversarial examples are an issue with modern machine learning. So what an adversarial example is if you have a classification network that correctly identifies that as a photo of a nodule, with 96% confidence, you can add a very small amount of what to you and I basically looks like popcorn noise and get a completely different answer, right? So these two inputs are clearly in the same domain, right? From a human and from an analytic perspective, the semantic meaning of those images hasn't changed at all. And yet the machine learning algorithm's output has completely flipped with an imperceptible change. And Athalia et al., there are some concerns, have been concerns in the community that it's a pathologic problem, right? This is a very particular popcorn noise. You can't just add random popcorn noise and get this change.
So
yes?
the first image is modified
Yeah.
If the second image is the correct one.
Original
one?
plus noise is modified.
Okay.
Yeah. So there were concerns that it was just a pathologic issue. So Athalia et al. Made this paper that I really like, where they actually 3D printed a turtle and they painted it. They uploaded images of it at different rotations and different lighting conditions to Google's image classifier, which always considered it to be a rifle rather than a turtle. And you know, clearly semantically that is a turtle. So this is a problem. It calls, you know, the features that the network's looking at into question, and B, it's a very real security concern. And these are really easy to generate. You just you know, the neural networks are just a math machine. You can calculate the derivative, which is a linear estimate of how the output's going to change when you change the input. And you just follow that derivative and you can make an adversarial example. You know, you could have just as easy made this look like an orangutan or a tree or whatever else, and it would still functionally to you or I look like a turtle. So, you know, this popcorn noise, this adversarial perturbation doesn't really line up with any of the explanation methods that I've talked about. So what that shows us is that these explanations, you know, they're mathematically verifiable at the exact input being considered. But the moment you change that input even a little bit, those explanations are garbage.
So yeah. The explanations actually change when you add the noise? The popcorn noise?
Yeah, they change. Yeah, and they're not very useful. It doesn't show a correlation. So we really have two flaws here, right? Existing explanations are a heat map. They just point to what's wrong. They don't necessarily express the quality at all. And they fail completely in the presence of adversarial examples, which demonstrates kind of how fragile these are. So the driving question, the real one question that my dissertation sought to answer was, is there a more reliable and informative way to describe what's going on in neural networks? Previous methods have issues. So sensory relevance models is actually an umbrella term. And what it means is an explanation method that uses the full richness of the sensory domain. So part of the issue with the heat map is it's just a mask. It just points at something. It doesn't have any color depth. So I wanted to look into techniques that would add color to the explanation and hope to coax out more meaningful explanations. So peek, the answer is yes, there is a better way, and the rest of this presentation basically talks about getting this more high-resolution, semantically meaningful explanation. So first, I want to cover my first attempt at sensory relevance models, and that was network dissection. So this was the majority of my original proposal, actually, was talking about this function. And in humans, there's a number of studies that if you just show a person input-output pairs and say, you know, learn the function, learn to reproduce that, it's hard. If you show the steps, if you show what operations you have to do along the way of that transformation, it becomes a lot easier. So this was kind of motivated by that, why rather than having just an input to output mapping, what if we bisect that network, split it up, and we produce an intermediate step that has significance? And here, the way that was going to be implemented was sparsity, so that most of the input wouldn't affect the final decision. So in this case, for example, only the bit highlighted by the green would be used to make the final decision, and everything else on the input would be completely ignored. This was somewhat motivated by literally removing the ability of an adversarial example to affect, right? If you change these pixels, then if you've completely filtered them out, they can't change the final decision. Attention models scale those pixels down, but they don't completely get rid of them. Adversarial examples clearly have high gain because you're adding a small perturbation, getting a big change. So, you know, a gain of 0, you can never recover from that. Looks like a heat map based approach. I was just talking about how those are flawed. Well, not really. Just like how full color images have 3 channels, red, green, blue, the sensory relevance model here would have depth. It's not just a mask. It has, you know, 32, 64, or even more features in that. And then you could cast from that really high dimensional space back to an RGB. So astronomers use this technique a lot. They measure different bucketed bandwidths of light emissions from distant celestial bodies, and they make a composite image out of those measurements. So it was going to kind of do the same thing here, was the idea. So that's one way it differs. The other is attention models. You just train the same way you train a normal neural network. You don't modify the training process at all. You just change the architecture. Here, because I'm completely filtering out part of the image, I needed what's called an auxiliary loss to allow learning in the places where information wasn't getting passed. So the way that works, neural networks are stacked linear operations and nonlinear activation functions, and the current state of the art typically uses this ReLU or rectified linear unit activation. What that does is, if you have a number less than 0, it just truncates it to 0. It throws away that information. And if it's greater than 0, it leaves it as is. It's an identity transformation. So what this is willfully throwing out information that is deemed unimportant and just kind of allowing the network to focus on the activations that positively affect the final change. And if you look at kind of a one-dimensional activation, you can imagine that sort of shape on the activations. And so what ReLU does is throw out everything that's below that 0 point and keep the stuff above. So there's a certain amount of sparsity built into existing neural networks. And what this did is basically move that surface up or down based on a loss, right? So you can target, in this case I used an integrating controller to target 26% activity, somewhat arbitrary, but as you're going to see in the results, it's enough to show a proof of concept. So what that means is I want 26% of this activation surface to be above the 0 point and 74% below it, completely filtered out. That's how we're going to get that sparsity that gave the little T shape. Yeah. So what you get is this. So on the left here, we have the input image. We've got a deer, elk, I'm sure, but it's lumped into the deer category, and an airplane. Here is the SRM output in the second column. You can see that it's very sparse, right? Most of the image is black. There are just like a few points that are done. Next to that is a dilation of the second column. So earlier I talked about convolutions being a fundamental operation in these neural networks. What convolutions do is they pull in neighborhood information, right? They pull in context from the pixels around these pixels. And so this particular pixel is based on, you know, a wider range of pixels in the original input. And it gets kind of downsampled through the process. So then the fourth column is the input image masked with that third column. In other words, any of the pixels that are masked out here that are black in the fourth column have no effect on the final classification. They were filtered out by the time you get to the network bisection SRM. So, you know, it's clearly, this method picks up features which from human intuition are relevant. You're retaining the antlers on the deer, kind of the snout, you know, the legs. On the airplane, you're keeping the wheels, the fuselage, the horizon. You know, you can justify that those are reasonable features to keep if you're throwing away 74% of the output. And, you know, ideally, since adversarial attacks can't do that, we're going to see a higher magnitude there, maybe get more meaning. This fifth column shows what this visualization would be like for a traditional network, just showing that the auxiliary loss did something. Proof of concept. If you do adversarial attacks about this and you measure the root mean squared error, which is basically the magnitude of that perturbation, there's no improvement at all. Even though it's on less space of the image, the overall magnitude is significantly smaller of the change, even though you're filtering out 74% of the input pixels. So you've reduced the surface that can be attacked, but on that smaller surface, attacks are more effective. So there's basically a gain factor that as you constrict the decision gets larger and larger, which really illustrates adversarial examples a bit. So, you know, at this point, it's back to the drawing board, unfortunately, for me. Fortunately now, but at the time, it was disappointing, you might say. So Alexander Madry et al. Proposed this saddle point formulation, which describes a classifier under adversarial attack, where the classifier is trying to do the best job it can by minimizing loss, while simultaneously there's this inner maximization problem of the adversary trying to come up with a close-by image that performs poorly. And what you can see here, X is the original input image, and this delta is the adversarial perturbation, is that hop-torn noise. And below the max here, you can see that delta is bounded by some space, capital S. This is another thing that I've added to the literature. So basically all existing methods bound S by some ball of perturbation, right? A maximum magnitude of 0.2 or whatever. And they look at the classifier's accuracy just at that single point. But that's not necessarily reasonable. If I have an image of a frog, I can turn that into an image of a truck, right? I can just take the image of the truck, subtract the frog, and I can add that back to the frog whenever I want to get a picture of a truck. And that is an adversarial perturbation, in which case it's no longer a frog, right? The actual underlying label, the semantic meaning of this image has changed. So if you don't bound the perturbation, then you can always get a meaningful change. So instead, I propose this algorithm 1, which basically moves frog towards being a truck, generates increasing perturbations in that direction, and then once the classification switches to truck, you then switch to minimizing the amount of perturbation. So you're basically skirting the boundary between frog and truck, trying to find the smallest possible change that will turn that frog into a truck. And then you can make a graph of how a classifier's accuracy will degrade as you get larger and larger perturbations. So here in blue, we have a traditional network with no adversarial considerations taken into account. You can see that it falls off very sharply. That explains why the input image doesn't need to be changed really to get a change in the output. It just changes too quickly. Madger et al. Here is what's called adversarial training. That's that saddle point. I'll talk more about that later. And my method, basically what it creates here is a very long tail. We'll get more into what that is. Yep.
So you're actually averaging between two images that it's been trained on. Both of them individually would give a correct classification. And the attack then is the
that would be a way
addition of the two, or
that would be a way to do it.
Okay.
Here you literally just follow the gradient. So you go from frog, you calculate the derivative for truck, and you follow that derivative. So you're not explicitly interpolating between two different images in the input, other than what the network has imprinted. Does that clarify that?
so yeah. So the frog is actually, if you input that image, it would be a correct classification.
Right.
Okay.
Right. And at some point, which for a traditional network would still look like a frog to you and I, it's going to switch to truck.
Yeah.
And the goal here is to minimize that. And you'll notice this is 10 to the negative third. So these are still pretty small changes, even for the past state of the art. And that's why the long tail is significant. I'm deliberately sacrificing accuracy on clean data. And I'll talk more about the benefits of that later. But what this plot gives us, what's nice about this is that we can make a single metric out of this, a single scalar number, which for engineers is easier to compare and easier to optimize, so that's nice. Accuracy robustness area, or ARA, is just the area between that curve, the accuracy as it declines over attack magnitude, and a naive baseline. So a naive baseline is just, if there are 10 output classes, it's a 10% chance that you're going to randomly get the answer here for this problem. And if you take the area between those two curves, you get a number that basically shows how resilient a classifier is across a whole range of perturbations. Before, people were just looking at like a sample point. They say S is the magnitude of 20 times 10 to the negative 3, and just comparing the accuracies at this point, which doesn't really capture the whole curve. So how can we maximize that, right? I have a metric now, want to maximize it. So what is an adversarial example from a different point of view? Machine learning networks end in this softmax operation, the exponential thing there, and what that does is takes an array of numbers bounded by negative infinity and infinity, that is to say unbounded, and converts them so that the sum of all those numbers adds up to 1, which is a probability distribution or a confidence thing, right? You want the sum of all your classes, 40% bird, 20% truck, and you want them all to add up to 100. So for ImageNet, which has 1,000 dimensions, if you set all of these little values, all of these negative infinity to infinity values to 0, then you get 0.1% confidence for each of them, 1 out of 1,000. If you move just one of those 1,000 values up to 10, which is arbitrary, then that class jumps from 0.1 up to 95.7. You can cut that value back to 3.8 and it falls all the way to 4.3. And then if you keep that the same and increase another one, it falls further and that other class goes up to 32.1. Suffice it to say, I'm just changing one number out of 1,000 each of these times. I'm not changing that number by a magnitude that is ridiculous relative to the original 10, and I'm getting significantly different classification likelihoods. So it really shows the innate instability kind of in this softmax operation and how these numbers relate to one another. And you can actually come up with an inequality if you assume that the network is locally linear and look for an expected change in your output in one of these values. You can relate that to the expected change in input times the amount of expected change in output per input. So you're just doing basically a first order Taylor series here or whatever, where you're just looking at the gradient and you can calculate what your expected change in output is. And if you evaluate this for real networks, the inequality holds. So what this shows us is that current equations are locally linear, and it allowed me to zoom in on that little guy, because if you decrease that quantity, then you're also decreasing the bound on the change in output. It assumes locally linear, but see how it holds up. So this is basically a form of Lipschitz constraint, which limits the slope of a function more or less. You can't do it directly. If you have a lot of GPUs, then it takes, say, a day to train that 1,000 class problem. I think it took me a week with 4 GPUs. You would have to do one of this operation for each output. So rather than 1 day, now you're taking 1,001 days to train a network with this technique. That's not really tractable. So what I did is a stochastic approximation of a more formal Lipschitz constraint, where rather than minimizing the partial of all these y1 to y1000, I'm just choosing one of them at random. And then minimizing that one. And you can minimize more than one, and what I showed in the dissertation is basically that it doesn't matter how many you're smoothing at one time. It's a stable approximation. Neither accuracy nor error is affected, but when you minimize that, when you minimize this derivative, this is the original input, right? Well, this is actually the adversarial example for a traditional, which looks like the original input. When you add the Lipschitz constraint, I'm not sure the contrast on the projector is high enough, but hopefully you guys can see that it's notably darker in the tumor area. And that's an example of an adversarial example that makes it more tumor-like. If you make it less tumor-like, what you can see is that it actually preserves some of the rib bones in that area and just starts to filter out the tumor. So in other words, just constraining that gradient, the change in expected change in output with respect to the input, has a practical effect on adversarial examples. Okay. Psi is the strength of that loss. So go back a minute. So there's this psi scalar, right, for the loss of adversarial examples. And in order to have the network learn what's a lung nodule and what's not a lung nodule, you also have to have a classification loss in there. And basically what this psi determines is which is more important, the original classification loss or the smoothness of the evaluation surface. So that's a very intangible quantity to deal with. It was annoying, so I have a fondness for integrating controllers, apparently. Used an integrating controller, and you can actually target a specific training loss and kind of increase the strength of the Lipschitz loss to maintain that level of training loss. And to show that this works, if you do a traditional network, you get an accuracy of 92.2% and an ARA of 0.0013. That's that thin blue line that just crashed into the horizon we saw earlier on the ARA graph. If you fix psi at 12,000, arbitrarily chosen, then you end up with a final loss of 1.007, Accuracy falls down because you've now added another constraint for the network. That is definitely something that future work should pay attention to, but for now we're okay with that because attack ARA, the area under that curve, jumped up significantly to 0.0125. If you, rather than fixing psi, you let it float, and you want your network to get down to the final loss, the same loss as the original, then you recover a few points of accuracy and you keep the same ARA. So what that means is it's reasonable to use an adaptive controller to control this strength of this loss. Furthermore, what this shows basically is that as you increase the size of the network, if you're not using an adaptive value of psi, you actually lose some of your adversarial resistance, whereas slowly ramping up that value lets you recover that. So basically no downsides to an adaptive loss, and it lets you hold one thing constant, the final training loss, while you play with other parameters on these networks. So explanations, I showed the tumor nodule already. Adversarial example, again, you basically just go up to where the classification changes and you hover around that border. While these networks are more resistant to adversarial examples, with full RGB images, the change is not as significant as I personally would like. It doesn't function as an explanation. It's still, you can change donut to sandwich here and it'll still more or less look like the input image. So as far as an explanation goes, as far as the original objective, that's not useful. But if rather than targeting a change in accuracy, you target a perturbation magnitude, you get features that may have meaning. So here, targeted donut with the positive explanation method, and you can see that it actually adds a hole in the middle of the sandwich. And not only that, you can see how the bright spot here lines up with the lighting on the edge of that hole. You can start to see how the features in this network snap together a little bit, right? So again, and this is also minimized, it's still that algorithm 1. So this is in some sense the closest image, the most donut-like image, which is a perturbation of 0.075 away from the original image. You can also do a negative explanation. You get a fire hydrant, not terribly useful. I think the positive explanations are much more informative. So the actual class for this is sandwich. And by showing a positive explanation for a sandwich, we can see a few interesting things that explain basically, they demonstrate training bias in this classifier. So again, machine learning, you have input-output examples and you say, go learn the mapping. So what this shows us is that if you want a strong likelihood of sandwich, you got to see that pile of ingredients from the side. Otherwise, the computer doesn't think it looks like a sandwich. Clearly, most of the images in the training set had this sort of stack of contents, and it also, again, projector contrast, it lightened up the bread a fair amount. So it's probably more like a sliced bread, maybe fewer pictures of a brioche bun. But again, this makes sense, right? Like if you look at that, and I asked you if it's reasonable to say that's a sandwich, I would contend that it is. And it shows these high-level features that actually get magnified by the network. You can also make the sandwich look like a horse, and it basically just shows legs. It is what it is. Yeah. So great, I have a method for increasing the ARA, and I have a separate method for explanations. Can you use the method for explanations without the ARA maximization? Not really. So if you take a picture of a particular cat on a traditional network and you perturb the image towards plain cardboard cat, you basically just get popcorn noise, showing that traditional networks don't have the expressiveness, they don't leverage the low frequency, high level features that you or I consider as semantically significant. They're just looking at these popcorn features. Interesting paradox, though, it is more generalizable. If you look at the accuracy of this network, it's higher than this accuracy on clean data. But the explanations on the network, which has had the Lipschitz loss applied to it, contain features which are more consistent with the classes that you're explaining. You get the wheels and the headlights on a car, you get the leg and the kiwi-style body on a bird, and you can see for cat, actually, which is interesting, It's mostly looking at the dark mass of the body and the shading on the ear. It's not actually necessarily paying too much attention to the same things as you or I, but it is paying attention to larger features, right? It's paying attention to the actual form of the object.
So one question is,
yeah.
You talk about the network bijection. So is that you using that technique through all of these analyses that you're doing, looking at the bijection output?
Do you mean Jetly, the attention model?
Yeah.
Okay, I am not looking at that at all.
Oh.
I actually haven't. I combined this in the document with the network bisection SRM because I had an implementation for it already. I did not combine it with the attention model, but again, if you combine it with the attention model, all you're getting out is that heat map again.
Yeah, okay.
And arguably, if you look at where the differences between the adversarial image and the original is, you could also generate a heat map, which would give you similar information, but you also get this high definition feedback. So yeah, we have explanations. I can tell you that one network is more explainable than another. Is there a number that actually predicts or correlates with how effective that explanation is going to be? It turns out there is, and this is a different version of the ARA, that accuracy robustness metric, called the better than random ARA. So an adversarial example, right? If you have two related classes, a car and a truck, and then imagine the other classes are bird, dog, organic forms. There are a lot of similarities between a car and a truck, right? If I cover the back of this image, you could almost say that that could be a truck. And so what happens in networks is that if you start with these two classes fairly close together, as you go through the training process on this image, it's going to be more likely to be a car. But since that shares features with truck, they're going to rise in tandem. The confidence in those two classes rises together. So the difference between them, which is all you have to do to get an adversarial attack that affects the accuracy of the network, doesn't really change much. And that's what the attack area is measuring, is basically the stability, the height of that red arrow. So what back to random does is you go to a fixed point instead, 1 out of 10 if there's 10 output classes. And you can see that the magnitude of that transformation becomes larger through training, even though a related class also becomes more confident. You're measuring the full size of that bar rather than the difference between the most confident bar and the second confident. And yeah. Okay. So if we look at networks, I'm stacked from smallest BTR ARA here of 0.0182 down to the highest of 0.0538. We can kind of see the progression and verify that BTR ARA does measure a network's ability to capture large-scale large-scale features. So the top one, again, a network without any of this adversarial robustness has a BTR ARA of like 0.001. So when you go up to 0.0182, we get structural features, but it looks more like a comic book. It's not necessarily anything dog-like. Since I didn't say it yet, this row is the amount of perturbation. So we're going from the original input image and allowing explanations of increasing magnitude as we go to the right. And as you increase in BTR ARA, you get a more cohesive explanation. Third columns, there's a difference between the two, but this one is definitely the most stable. I'll put it that way. This is the only one where the final column actually looks like a not perverse dog. The second one has a separate stability added, which might explain why to you or I it looks more cohesive. The BTR ARA here is lower, though, probably because the significance of the feature, the actual scale of the features that the network is latching onto, is smaller. This one looks grotesque. I wouldn't argue it's a good dog, but it is a larger scale change to the image. It's incorporating more information from the whole image. So BTR ARA is a correlation basically between the smoothness in the size of the features and the cohesiveness of the explanation you're going to get out. So I did other things. The half-Huber ReLU. So traditional networks, they optimize just the value of the network. With the Lipschitz loss, you're actually optimizing the first derivative of that network, so you're looking at the second derivative. The ReLU activation function has a continuous value, but a discontinuous first derivative. So since I'm optimizing that first derivative, it seemed that it would have merit to make it a continuous. So the half-Huber ReLU has a continuous value and first derivative and a discontinuous second derivative, and it is very helpful. So when you add the half-Huber, you get a lot of accuracy, you get some resistance to adversarial examples, but interestingly, you lose some of the BTR ARA. Then if you do an ablation study though, so I got a lot of accuracy by adding the half-Huber, probably because it eases the optimization process. So if you decrease the strength of the Lipschitz loss so that you get about the same accuracy on a network that is not using the half-Huber ReLU, then you have lowered both attack and BTR ARA. Again, all of these techniques, you're willingly sacrificing some accuracy. So that's, again, part of why I wanted to target a final training loss. This is all fixed psi, but the adaptive psi kind of lets me hold this accuracy column constant and just look at how stuff is changing attack and BTR ARA. You can also use uneven stochasticity. So before, when I talked about the stochastic Lipschitz constraint, you pick one of the outputs out of 1,000 at random with a uniform distribution. Well, you don't have to do that, right? A picture of a car has more information about a car than it does about an orangutan. So maybe it makes sense to smooth the car prediction more often than the orangutan prediction. Use zeta for that. And you can see here the accuracy is about the same. It is a little lower, but the other constants go up. And I'm not actually too worried about that decrease in accuracy because you can also, when you do uneven smoothing, go a step further and do what I've called tandem smoothing, where, again, this is working off the BTR area theory of as you train car, you're also increasing truck because shared features. And so rather than leveling car on its own and making that a stable representation, you can stabilize the difference between the car and truck representation. And what that does, it turns out, is let car differentiate itself a little more. You see that in a higher attack ARA, also higher accuracy, and you gain even more BTR ARA. So that's cool. Adversarial training, that is the previous state-of-the-art in adversarial resistance. So here up top is kind of a better picture of what that's actually doing to the decision surface. If you have a data set, 2 points here, the optimal machine learning solution doesn't say anything about what the decision surface should look like between those points, right? You just need a line that goes through those points. It doesn't matter how it goes through the points. It's nailing the training set perfectly. If you add noise, you start to get some smoothness around those points because you're allowing the network to train on things in the neighborhood, but you're not necessarily always going to the worst case. The reason adversarial training works so well is because you're always going to the worst case solution. You're kind of stamping out these problem parts in the network's decision surface. Now, it's still not a smooth surface by any measure, but it's markedly better. And that's actually why, and the theory in this paper kind of demonstrates why adversarial training is effective, and it's because it steps up this BTR ARA metric. And when you add Lipschitz, you're not only smoothing the surface per value, but you're ensuring that between points is a more smooth connection. So if you add adversarial training, you lose some accuracy, and you get mostly attack ARA, a little bit of BTR. If you then add the Lipschitz to that, again, willingly sacrificing accuracy, you get a huge bonus in the overall robustness of that classifier. So remember, this accuracy column is just on clean data. No perturbation at all. If you allow any perturbations, then the network with both Lipschitz and adversarial examples is significantly better. Even though it's worse on clean data, it's much better once you allow perturbations. And a much, much higher BTR ARA than the previous state-of-the-art. And if you then take out the adversarial training and just do the Lipschitz, then you lose a little bit of attack and a little bit of BTR ARA. Again, that's because you're not seeking out the problem parts, right? You can smooth the surface at the data points, and the neighbor can still not be smoothed. So this is a demonstration of the explanations through these different techniques. The top one is a traditional network. Again, not really helpful. Next is adversarial training. What this shows, again, is that BTR ARA, what it means to have a lower value. So the snout of the dog here in the input has basically 2 eyes and a muzzle of its own. And the adversarial ARA, the adversarial training, the explanation method, the adversarial explanation method of pros basically demonstrates that that's the feature that's being accentuated, right? It's not actually looking at the whole dog head. It's looking at the tip of the snout and saying that could also be a dog face. Let's run with it. If you add the Lipschitz constraint to that, then you're using much more of the whole image. You're using basically the overall shading on the feature. You do get this little slightly strange looking multiple eye in the eye sockets, but there's a, it's using the overall thing. From a human point of view, this is the most adorable explanation, but it's still only using the left side of the face. So the BTR area here is lower than this one, and there's definitely a more recognizable feature there, but it's not using as much of the image. It's not using kind of the high-level features in that image. Human in the loop, talked about that. So first off, this explanation technique gives a human operator a better idea of what's going on in the network. It shows what the type of features the network's actually looking at, but it's not human in the loop yet because you haven't actually then you haven't actively improved the network. So what I wanted to look at, of course, is if you can use these explanations to then improve the network training. So built this little web interface, which basically just takes an input. Here's of a dog, generates an adversarial explanation, and the annotator can say if it's still in the original class or if it's something else. And some of these, if you look here, the adversarial explanation is not really different for this particular truck for whatever reason. So the annotator would say, hey, that's still the same. And if you do this, my colleague Jack Chen labeled like 2,000 of these, I think. Yeah, he labeled 2,000, and I labeled 730 or so. So if you do that, and you take the ones that didn't change, so where the adversarial perturbation is still the original input class from a human point of view, if you then add those to the training set, and you retrain a network, you actually get some gains in terms of both attack ARA and BTR ARA. The amount of gain there doesn't look super significant, but I will point out that the original data set had 50,000 examples, and we're only adding 1,000 to that, so we're adding about a 2%. We're adding about 2% to the size of the data set and getting around 3% gains. So what this shows basically is that if you already have a bunch of data, this technique may not add a lot, although it does stabilize some of the explanations. This bird has less weird of a little jut there. The cat's more of a whole cat than just a face, so you could have some argument there. But for smaller data sets, this is a fairly promising technique to extend your training data. And you can do this multiple times. We didn't because it takes a while to annotate, but you could. I did other stuff not related to this. I really wanted to focus on the adversarial explanations for this presentation. But I also implemented network bisection SRMs another way through what's called gradient integration modules. I actually improved adversarial training on its own by 17% by designing a better adversary. I worked with OHSU a little bit on their MEP-Links project, which is basically a database of pictures of cell cultures which have been treated with different ligands. And they want to answer, what is the difference between treating cells with 2 ligands? Like, what's the dominating feature if I treat it with one ligand over another? And adversarial explanations can kind of help with that. extended my master's thesis work, the simple spiking locally competitive algorithm, to include inhibition, and produced hardware which used 1% of the energy and had 21 times the throughput of previous ASICs in the sparse coding field. I demonstrated the LCA dictionaries, which is another sparse coding thing, can be trained as a supervised task rather than just unsupervised, which was the previous modus operandi. I proposed other hardware for efficient machine learning, data centers burning down the rainforest and all. So I proposed 4 different vector matrix multipliers, which is one of the fundamental operations in machine learning, and looked at a reservoir computation technique for atomic switch networks in collaboration with UCLA. On all, I published 8 peer-reviewed papers and 6 non-peer-reviewed proceedings. Conclusions. So, state-of-the-art explanations had 2 flaws, really. One is that they all use heat maps, basically. They point at a problem but don't tell you why. The other is that they don't explain adversarial examples. I showed that network bisection SRMs, even if you eliminate and completely filter out 76% of your input space, you don't really provide any resistance to adversarial examples at all. Showed the ARA metrics, that you can basically look at how a classifier changes as you allow the attack space to increase. Added network modifications that increase the attack ARA, the robustness in the presence of noise by 2.4 times, and significantly improved the BTR ARA by about a factor of 3 compared to the state-of-the-art on ImageNet, which is that 1,000 class thing. Showed that adversarial examples themselves can be used to make high-quality explanations, which solves both flaws, right? You're working with adversarial examples now, so the problem's solved innately at a point. And it's much higher definition than a heat map. And I showed that you can use those adversarial explanations in a human-in-the-loop training cycle to squeeze extra performance out of your classifiers. And that's about that. Thank you. Questions?